This is the essentials of sonographic principles and instrumentation. We're going to go through this first section. There's a couple of things I want to mention before we get to the main portion of the talk. First off, I want to thank Don Milburn for allowing me to use so many of his slides from his past lectures. I certainly couldn't have put this together without his help, so thank you, Don. Appreciate that, and I appreciate all the videos that you've given me over the years. The Schiller-and videos are courtesy and all rights are protected. Unapan, Cindy, and Don made these videos in Wauwatosa, Wisconsin at the General Electric Ultrasound Research and Development Lab. So ask yourself, why do I need to know physics? Can I be a good sonographer without really understanding all of these physics concepts? And the short answer, the only answer, is no. Why? Because this improves patient care. And certainly the best interest of the patient is the only interest to be considered. So I have a disclaimer. I have no conflicts of interest to disclose. This is a review session. It is meant to be an in-depth ultrasound physics review. You should already be familiar with the ultrasound concepts so you can get the most out of this. The quote workbook edition of this program does not include all of the graphic clips you see in the live presentation. Some of them are proprietary and or do not reproduce adequately. So open your mind, relax, have fun. We are going to learn a little bit about ultrasound. But first we have to discuss the rules. And the rules are the rule of threes. I'm going to mention all of the principles at least 3 times. If you don't catch or understand something the first time I talk about it, don't worry, you'll hear it explained at least 2 more times. The rule of 2s is that everything in ultrasound has at least 2 different names. There's no unified dictionary. You have to learn all the synonyms and varieties of terminology. This is because these different terms were often created by manufacturers who were competing against each other and wanted to have special terms for what are essentially common machine functions. So some of them will say that they have a persistence button, others will say, oh no, we use frame averaging. Well, it's the same thing. Others have color threshold, color priority, it's the same thing. You'll hear some manufacturers talk about compound imaging, which is the same as crossbeam in GE machines, and Sono CT in, I believe, Siemens or Philips. These are all the same types of synonyms for each other, and unfortunately they've become part of the vernacular, and there is no settled language that we use for ultrasound. So we use their manufacturer names for compound imaging as well as just straight out calling it compound imaging. And then first, in order to pass the SPI exam, you need to understand some concepts of sound, the relationships of sound, the system components that produce and control sound, the various terminologies that are associated with sound, and you need to know quality assurance for ultrasound labs and clinical safety. And so we're going to look at these when we discuss the ARDMS exam content, but these should be what were covered in your physics course. If they weren't, then perhaps you need to look at where you took your physics. So change your attitude, open your mind, don't let physics scare you. The definition of physics is the branch of science concerned with nature and properties of matter and energy. Ultrasound is energy. You're part of nature, you're made up of matter, and sonographers are concerned with energy. It's all simple, right? What does the term physics mean to someone using ultrasound? Well, it means everything. It is, let's see if we can get that going. There we go. The more you learn, the more you're going to appreciate ultrasound physics and how you can use this to solve problems in the clinical setting. So all imaging is done using physics, and so to improve your imaging, you're going to need to understand how to do that. Now let's talk a little bit about the SPI exam. And the SPI exam, or Sonography Principles and Instrumentation, is put out by the ARDMS, and they have certain things that they want you to learn. Clinical safety, patient care, and quality assurance are foremost in their list. Physical principles, of course, you would assume that would have something to do with the physics review. Ultrasound transducers, imaging principles and instrumentation, and Doppler imaging concepts. Now, two of these things within this, quality assurance and new technologies, we're going to set aside till the end because we really don't want to talk about those until we've given you the foundations on which to build those new technologies. And of course, you're going to need to know something about bioeffects before we talk about quality assurance. So let's start out with the first part, and that's patient care and what we need to know about patient care in the ultrasound lab. We're going to start out with clinical safety. And you don't want to injure your patients, so clinical safety is the most important thing we can start with. You must be able to apply the general accepted infection control and precautions and disinfectant techniques to ultrasound equipment. Anybody who has now lived through the COVID pandemic is probably getting really good at these infection control precautions and disinfectant techniques. And if you're not, you're one of the statistics. Need to understand ergonomic techniques in order to reduce what we call WRMSD, work-related musculoskeletal disorders. So ergonomics is part of the SPI exam, and protecting yourself from work-related musculoskeletal disorders is part of your career, because if you don't protect yourself, you're going to have a darn short career. Several of my graduates got out of the school, went out and practiced, and within 2 years they were not able to lift their arms and work anymore. So please follow the ergonomic techniques that you've learned. Make sure that you apply them on a daily basis. Make sure that you take the time to relax your muscles and stretch after each exam. You need to understand how to modify power output and follow the ALERA principle. ALERA means as low as reasonably acceptable. Need to be able to identify potential bioeffects. Are you going to be causing bioeffects in your patients? I sure hope not. How are you going to know that you're not? Well, we'll talk about that when we get to it. Here's a sample SPI question on ergonomics. What is ergonomics, and what percentage of sonographers experience MSK injuries at work? The answer is ergonomics studies the interaction between the sonographer, patient, and equipment to minimize work-related musculoskeletal disorders. At the time this question was written, 75% of sonographers reported scanning in pain. That number has actually gone up quite a bit since then. If you want to learn more about work-related musculoskeletal disorders and how to prevent them, you need to learn about REBA and RULA. So REBA is the Rapid Entire Body Assessment Tool. RULA is the Rapid Upper Limb Assessment Tool. Google REBA and look for this chart under Images, and you'll be able to download that, and you can follow exactly what to do in order to be safe with your entire body. Don't look for this REBA. She's on a different schedule than what we're following. Clinical safety includes patient identification and documentation, making sure that you follow your lab protocols. Great care should always be taken in positively identifying the patient, checking the name and ID, birthday against all documentation and examination requests. There's probably nothing more embarrassing than doing a transrectal exam on a patient that you just got from the ER and finding out that you did it on the wrong person. Verbal as well as written ID documentation is the standard protocol. Make sure you follow the 4 W's. What is your name? What is your date of birth? What is your address? What is your doctor's name? What exam are you here for? Laboratory procedure and protocol manuals should contain current updated data on universal precautions as well as current emergency situation protocols. If your lab doesn't have that, then you need to become in charge and take care of that and get it fixed. Because believe it or not, you're still going to be responsible whether they did it for you or not. Here's a sample SPI question. Patient is brought to your lab for ultrasound testing. The patient is sedated and has no ID band. The examination request has patient information, i.e. the name, date of birth, etc. What do? A, do you do the requested exam? B, request the patient to be returned to the ward for positive ID and banding? Get a verbal ID from the person who delivered the patient? Or just ignore the problem and hope it resolves itself? Well, I hope everybody is looking at B and knowing that you must request the patient to be returned to the ward for the person in charge up there to positively ID them and band them. Let's move on to something that most of you don't like, and that's math. Math is universal subject that ultrasound students have hated forever. But why do we need to know math? Well, we have lots of numbers on our machines, and we have to know what those numbers do, every single one of them. These things only work one at a time. If you can't explain and you don't know what every single number on your system display is, then you need to go study some more math. Because you need to know what everything on the display is referring to. That is your job, part of your job. However, you don't need to be a math whiz in order to do that. You don't get to use a calculator on the registry exam, and you do not need to be able to solve complex equations with ultrasound physics. You do need to know concepts, and then you'll know the answer. So the math on the registry is very simple. So if we increase our frequency, if we double our frequency, what happens to the period? Questions like that are what we're going to run into. If we increase depth by a factor of 5, what happens to the frame rate? Okay? So these are all relational mathematical questions, and you have to know how they relate to different parts of the ultrasound machine and imaging. 1/2 of the PRF is what? Well, it's the Nyquist limit. We often say that mathematics is made up of variables, but in reality, the variables are what make up our everyday existence. And what are variables? Well, variables are just simply things that can change. Variables can be unrelated to each other. In this case, X is unrelated to Y, just like temperature is unrelated to what day of the week it is. It doesn't matter if it's Wednesday, that's not going to tell you anything about the temperature. And knowing the temperature is not going to tell you anything about what day of the week it is. Hair color has absolutely nothing to do with a person's weight. So you can have any color hair you want, purple perhaps. It's not going to tell somebody how big you are, how much you weigh, how small you are. But variables can also be directly related to one another. In the example where X increases, Y increases by a similar amount, such as if the temperature goes up, the pressure goes up. Okay, that's a direct linear relationship. The age of a child is directly related to the weight of a child. Obviously, a child who's 1 year old is going to be smaller than a child who's 10 years old, for the most part. Variables can also have inverse relationships, so as one goes up, the other decreases, such as as your grades go up, the time you spent at parties will have to decrease, vice versa. As your time spent at parties increases, your grades will go down. As your spending goes up, your money goes down. Everyone can relate to that one. And as your speed increases, then your travel time decreases. So we know intuitively of certain variables that are inversely related to one another. Then there's a special case of variable called the reciprocal relations. Reciprocal relations are when two factors are multiplied together and the result is equal to 1, such as 2 and the number 1/2 are reciprocals. You multiply them together, you get 1. 10 and 1/10 are reciprocals. Units can also have reciprocals, and you need to know these that apply in ultrasound. The unit seconds has the reciprocal hertz, or cycles per second. The unit period has the reciprocal relationship with frequency. They are reciprocals. The period is the reciprocal of the frequency. And just as you have to be able to take units and understand their reciprocals, we also have to be able to take units and convert them to other types of units, such as if you took minutes, you have to be able to convert that to hours. 60 minutes is 1 hour. 100 pennies is $1. Now, when you're converting units, they must be the same type of units. So money, pennies and dollars are both money. Minutes and hours are both time. So we can convert them back and forth. You certainly can't convert hours to pennies, unless you're working, I suppose. So types of conversions that are commonly seen in ultrasound on the SPI exam is converting something like the speed of sound at 1540 meters per second into what is the speed of sound in kilometers per second. Well, it turns out it's 1.54 kilometers per second. What if you had to convert that 1540 meters per second to millimeters per microsecond? Well, again, it's 1.54 millimeters per microsecond. That's equivalent to the same speed as 1.54 kilometers per second. How about if you had to convert 3 megahertz to hertz? Hertz. That's easy. 3 megahertz is just 3 times mega, which is 10 to the 6 or million, in hertz. So you multiply them together, 3 million hertz. How do we do these conversions? Well, it's not too hard. You treat conversion factors as fractions with a value of 1 and carry the units. So we know that 12 donuts equals a dozen. We can put them in this relationship, 12 donuts over 1 dozen, and that's going to equal 1. So how many donuts are in 4 dozen? Well, you put them in the relationship. We wanted to know how many in 4 dozen, so we put 4 dozen times 12 donuts per 1 dozen. The dozens cancel, and we're left with 48 donuts. That's it. It's not too hard. But you do have to be able to do this in different ways. So let's do an example here. 1 hertz equals how many hertz? Hopefully you got the answer of 1. 1 kilohertz equals how many hertz? Well, kilo is equivalent to 10 to the 3, and 10 to the 3 is 1,000. So 1 kilohertz equals 1,000 hertz. Just as 1 megahertz equals 1 million hertz, and 1 hertz equals 1/1000th of a kilohertz, or 0.001 kilohertz. The metric system is set up so that we can do these type of unit conversions very easily. It's set up on the basis of powers of 10, and it uses scientific notation in units to handle very large or small amounts. So we have the example of 1,000,000 is equal to 1 times 10 to the 6 in scientific notation, which is equivalent to 1 mega. 1,000 meters is equivalent to 1 kilometer, kilo being thousands. And so 1,000,000 hertz is equivalent to 1 times 10 to the 6 hertz, or 1 megahertz. Now it's important for you to recognize in this picture that I have here that 10 to the 3 and 10 to the minus 3 are reciprocals of each other. So therefore kilo is a reciprocal of milli. Mega is a reciprocal of micro, and giga is the reciprocal of nano. With metric units, we often relate physical properties by using reciprocals. So the reciprocal of frequency is period. Therefore, if our frequency is 1 megahertz, what is the period? Well, it's 1 over 1 megahertz, and we can bring the mega up to the top as its reciprocal micro, and hertz up to the top as its reciprocal seconds. And so we have 1 over 1 megahertz is equal to 1 microsecond. Mega and micro are called complementary units. If the pulse repetition frequency is 4 kilohertz, what is the pulse repetition period? So we just write it out. 1 over 4, take the reciprocal, 1 over kilo, reciprocal, 1 over hertz. We're going to take the reciprocal of each of these. Reciprocal of 1 over 4 is 0.25. Reciprocal of 1 over kilo, if we go back to our chart, is milli. So we put milli in. The reciprocal of seconds, or hertz, is seconds. So we have 0.25 milliseconds. Pretty straightforward. So our last example using math, if the frequency is 5 megahertz, what is the period? Well, we just simply write it. 1 over the frequency, that's going to be the period. That's 1 over 5 megahertz. 1 over 5 is 0.2. 1 over mega is micro. 1 over hertz is seconds. So we get 0.2 microseconds. Now one thing I want to show you is that hertz here is written as hertz in this portion, and then I rewrote it as 1 over seconds, because that's what hertz is it's the reciprocal of seconds. And I just put it into the equation as its base unit. Now, how do I know whether or not I end up with seconds or 1 over seconds in the final answer? Well, it's fairly simple. If I have an even number of bars above my unit, then it ends up in the top. If I have an odd number of bars over my unit, it ends up in the bottom. So if I had 1 over 1 over 1 over 1 over seconds, I could figure that out pretty easily. That would be 4 bars, and it would just be the units of seconds. So that concludes our introduction to the ultrasound, and we'll pick up next time with looking at more physical principles